Welcome to the cell potential video. By the end of this video, you should be able to calculate cell potential from standard reduction potentials, and you should understand the relationship between cell potential, equilibrium position, and free energy. Let's start by defining cell potential. Cell potential is the pull or driving force on the electrons in a cell. It's also known as the cell voltage, which I'll be using interchangeably with cell potential. So imagine a voltaic cell shown here. The electrons move through the cell from anode to cathode. And here we've put in a voltmeter to measure the driving force on those electrons, or the voltage, or cell potential. We can calculate cell potentials by using the standard reduction potentials of the two reactions in the cell. A standard reduction potential measures a metal's tendency to gain electrons or to get reduced. The higher the reduction potential of a metal, the more likely it is to get reduced. You can literally think about this as what is the potential that reduction will occur. The higher the potential, the more likely it is to get reduced. Therefore, it's also more likely that that metal will act as a cathode in a cell. Of course, this will depend on what it's paired with, but as long as it has a higher reduction potential than the other thing it's paired with, it will act as the cathode. The cell potential, then, is equal to the sum of the reduction potentials for the anode and the cathode. That equation is shown here. Here's a standard reduction potential table. Notice that this gives the reduction potential for each of these reactions. So how do we use these reduction potential values to determine the cell potential? Recall that reduction potentials describe the likelihood or the potential for a metal to be reduced. Therefore, the higher the reduction potential, the more likely the element is to be reduced and the more likely it is to act as a cathode. Since all of the half reactions on a reduction potential table are written as reductions, we have to determine what will be oxidized and then reverse that half reaction. According to Hess's law, when we reverse the half reaction, we also change the sign on the reduction potential. For example, here's the reduction of manganese. If we want the oxidation of manganese, we would reverse the reaction and also change the sign on the reduction potential from negative to positive. It's important to note that unlike Hess's law, when we multiply a half reaction by an integer, we do not change the reduction potential. This is because reduction potential has a non-stoichiometric relationship with the reaction. Here's a visual representing these ideas. Here we see high reduction potentials at the top. These are elements that are likely to be reduced and act as cathodes. They are unlikely to get oxidized. As the reduction potential decreases, they become less likely to get reduced and act as cathodes and more likely to get oxidized and act as anodes. Let's do an example. Let's calculate the voltage of a zinc-copper battery. The reduction potentials are shown here. The first thing we need to do is determine what element is oxidized and what is reduced. Looking at the reduction potentials, we see that zinc has a much lower reduction potential. Therefore, copper is more likely to get reduced because it has the higher reduction potential and more likely to act as the cathode. Zinc, then, is more likely to get oxidized and act as the anode. Given that information, we reverse the reduction of zinc to show the oxidation of zinc, and we flip the sign on the reduction potential. From there, we can add the two potentials together. This gives us a cell voltage or a cell potential of 1.1 volts. Here's an example to try on your own. Pause the video here and answer these questions. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. First, I used reduction potentials to determine that aluminum would get oxidized and act as the anode, and cobalt would get reduced and act as the cathode. This is based on their reduction potentials. This is an interesting example because both reduction potentials are negative. However, aluminum's is more negative, making it less likely to get reduced and more likely to get oxidized. From there, I wrote the balanced redox equation, considering the number of electrons that were transferred. And finally, I calculated the cell voltage. Notice I flipped the sign on the aluminum reduction potential, but I did not multiply anything by an integer, even though I had to multiply by integers to balance the equation. Again, this is a non-stoichiometric relationship. Now let's relate cell potential to delta G and spontaneity. Consider the following two reactions. Will they both be spontaneous? Well, if you look closely, you'll notice that the second reaction is the reverse of the first. Therefore, it's impossible for them both to be spontaneous. If one is spontaneous, then its reverse must not be spontaneous. Considering the reduction potentials, however, we can tell that zinc is much more likely to get oxidized than copper. Copper is much more likely to get reduced. Therefore, the version of this reaction that shows copper being reduced and zinc being oxidized is going to be the spontaneous version of this reaction. The other version is going to be non-spontaneous. We can support this by calculating cell voltages. The cell voltage for the first cell would be a positive value, whereas the cell voltage for the second reaction would be a negative value. This supports the idea that a spontaneous process will have a positive voltage. So as we just said, spontaneous processes will have a positive cell potential or a positive voltage. That also means that they'll have a negative delta G. As we know, spontaneous processes have negative delta Gs, or negative free energy changes. We can also conclude that the more negative the delta G is in value, the larger the voltage will be. This is supported by the equation shown here, which is on your equation sheet. In this equation, F is Faraday's constant, also on your equation sheet, and N is the moles of electrons transferred through the cell. Notice again that the more negative the delta G value is, the higher the voltage will be. Now let's relate cell potential to equilibrium position. Note that functioning voltaic cells are not at equilibrium, but we can think about what happens as they move towards or away from equilibrium to help us understand what's going on. Since cell potential is positive and delta G is negative, we can assume that the equilibrium constant is very, very large, much, much greater than 1. Because when equilibrium is achieved, we'll have a very product-favored reaction. Again, this is indicated by the fact that we have a negative delta G, so it's very spontaneous in the forward direction. Let's consider a standard cell in which all solutions have a concentration of 1 molar. What would the Q value be for that cell? Well, let's consider this cell here. Again, if it's standard, then both solutions are 1 molar. Our Q expression is going to be the same as our K expression, in which we'll take the concentration of products over reactants, not including solids. So essentially, we're left with the concentration of the anode, which is the zinc 2+ in this case, over the concentration of the cathode, which in this case is the copper 2+. Solving, we get a Q of 1. Notice that this is not a very large number. Therefore, we are not yet at equilibrium. We can also infer, though, that the further the cell is from equilibrium, the smaller Q will get. If we move further and further from equilibrium, in other words, in this case that would be in the reverse direction, we will be increasing the cathode concentration and decreasing the anode concentration, thereby decreasing Q. This also means that our delta G is getting more and more negative. The reaction is getting increasingly spontaneous, increasingly thermodynamically favorable. This also increases the cell voltage. Now let's consider what happens to Q as the battery runs. As the battery runs, the system moves towards equilibrium. Consider the reaction here. It's proceeding in the forward direction. Therefore, we're increasing the concentration of zinc and decreasing the concentration of copper. This means we're increasing the anode concentration and decreasing the cathode concentration. Therefore, we are increasing the value of Q. This means Q is getting closer to K. We're getting closer and closer to equilibrium. This also means that delta G is getting less and less negative as Q approaches K, or as we get closer to equilibrium. Therefore, the reaction will be increasingly less thermodynamically favorable. It will be less spontaneous. This will cause the voltage to decrease. The voltage will continue to decrease until the cell reaches equilibrium. At equilibrium, recall that Q equals K. At that point, delta G will be 0, there will be no net reaction, and most importantly, the cell voltage will be 0. We commonly refer to this as a dead battery. We can look mathematically at this as well. Recall we've already looked at this equation. This portion of the equation can also be found on your equation sheet. The important takeaway here is that the more negative delta G is, the higher the cell potential and the larger the K value. Let's summarize this information in a table. As we've said, a negative delta G value indicates a spontaneous reaction. This will give us a positive cell voltage, and Q will be less than K because we're far from equilibrium. A positive delta G value indicates a non-spontaneous reaction and a negative cell voltage. In this case, Q is much greater than K. Also recall that when Q is greater than K, the reaction will proceed spontaneously in the reverse direction. Therefore, the reverse reaction would have a negative delta G and a positive cell voltage. And of course, when delta G equals 0, that means we have no cell voltage, no cell potential, and Q equals K. That means the system has reached equilibrium, there's no net reaction, and the battery would be said to be a dead battery. That brings us to the end of this video. Let's review our goals. First, we learned to calculate cell potential by adding up the reduction potentials of the two half reactions. Then we looked at the relationship between cell potential, equilibrium position, and free energy.